So welcome back to an introduction to digital technologies. This is the third part and the last video. In the first two videos, we learned all about the difference between analog and digital computers, and we learned about binary, about how to count in binary and convert them to decimal. In this video, it's all about computer languages and programming them. A general purpose computer is very versatile and you can do many different types of activities and solve many problems. In Tech Mandatory, we use computers to enhance the design process. And due to the computerization of nearly every industry, we want you to know how to program computers because there is an expectation that most jobs in the future will use some type of programming application in the everyday work. In terms of design, you can design nearly anything using software, and you may be familiar with companies like Adobe, Autodesk, Epic Games, that is, Apple and Microsoft. So if you've used any pieces of software from those companies, I'd like to know. Please leave a comment below about what type of software you like. A computer is described as an information processor. Its task is to take the information you give it. It thinks about it for a while and then shows you the results. Do any of you remember what these three activities could be? When the information processing occurs, the computer takes an input, it then thinks about the input and then shows you the results. So digital computers use a processor and they also use a long and short-term memory system to perform all the tasks. The processor does the thinking and the memory is needed to do the thinking. So you can't really have thoughts without having some form of memory. And the combination of these two systems sort of relate to our brain, as you might have seen in the previous videos. If this is like our quick brain, then what we will find is a lot of the thinking occurs in this part of the brain, and we have a short-term memory that's sort of in the middle here, and our long-term memories, they're all sort of all scattered in lots of different places, good backups happening there. But a digital computer is very similar in that process. The thinking part of the computer is often called the central processing unit, or CPU for short, and I'll just call it CPU from now on. So the CPU makes decisions about any apps that are running in the foreground and background. That might be a bit of a new concept for some of you, but you need to understand that when you turn a computer on, the operating system loads up, and that might be Windows or OS X or iOS or Android. And the operating system kind of is a whole lot of apps all running lots of different things. And when you go to load up an app like Google Chrome or Instagram, what really happens is the processor is saying, okay, I'm going to give you a little bit of time, I'll give you a little time, and it delegates little chunks of time to all the apps that are running. And if you're on your phone looking at Instagram, well, in the background, the Android or iOS operating system is managing other things, like there's an app running in the background that's waiting to receive a phone call or a text message or other messaging. And there's another one to monitor the battery and another one to look at the brightness. So there's lots of different apps running, and you really need this sort of manager of the CPU to take care of all those tasks. If you don't have that sort of device, then your computer can't really be a general purpose computer. And of course, the CPU can only do this if it's got some memory in which to store like what app is currently running and what one comes next, what one has just been, those sorts of things. So the CPU works in conjunction with the memory. So what I'd like you to do is just a bit of a thought experiment and imagine for you what it would be like to not have any memory. And I know I can feel like that sometimes, but if you just imagine our bodies are constantly receiving lots of different senses, and those senses travel along nerve pathways up to the middle of our brain, and the brain sort of interprets all of those signals. Now it needs to interpret them by relying on memories, and if there's no memory to interpret, then it's pretty hard to make sense of the world, because all of our sense is built from memories of past memories, which is kind of a deep idea to have. But if you think about it in more practical terms, we probably couldn't walk or talk, right? In order to walk, we need the memory of our balance. And in order to speak a language, we need to know the nuances of the language and different words that are able to express ideas and behaviors. So when sometimes people are unable to use their memory, and you may have heard of the term, it's called amnesia. So if you remove the memory from your computer, then your computer would also have amnesia. So it's crucial. Memory is so important to the CPU. And it was only in the last 20 years or so that memory has become very, very cheap. There's been a huge adoption of computers everywhere around the whole world because they've become cheaper. But prior to that, looking at 50 years ago or earlier, most people didn't have computers, and they were only really used by large government organizations, military, and in academia, in universities. Let's now investigate the memory of a computer system, and all this is going to help us understand programming. So the computer memory has 3 types. There's ROM, RAM, and the HD. So what are these things? Well, ROM is short for read-only memory, and this is a special type of memory. It's usually kind of small. It's the first memory that gets activated when the computer wakes up. So if you think about turning a computer off, that's sort of like the computer goes to sleep and it will lose all of its short-term memory. Like if I say the number 161285, some of you will remember that number for the next 5 minutes. And if I was to ask you to repeat that number again in a week's time, most of you would have forgot it unless you commit it to a long-term memory. So read-only memory is like a long-term memory, but its problem is that it can only be written once. So once you write into the memory, then it's pretty hard to erase it. You can erase them nowadays, but it requires a bit more effort. And inside the ROM are instructions for waking up. So it might be something like, open your eyes and sit up, then get out of bed, go to the toilet, wash your face, that sort of thing. It tells the computer what it needs to do in order to start the new day. You can't use the ROM because it can only be written once, right? It's read-only memory. Next we have RAM, and RAM is pretty much, I think, the most crucial part of the memory system, because if you don't have RAM, then the computer can't carry out the task, right? The current task at hand, that is. RAM allows you to have complex things going on, lots of things going on. Usually the more RAM you have, the more programs you can have running at the same time, and the more apps you can have running at the same time. RAM is still kind of expensive, and the CPU and the RAM are like best friends, they're BFFs, and they share a lot of the information between them. If you turn the computer off, if you put the computer to sleep, it will lose its contents. So when I say put the computer to sleep, I really mean if you pull the power out, not if you suspend the computer. That's a different concept. But if you turn the computer off, if it loses its electricity, then everything inside the RAM gets lost. Okay? And it's for that reason that you need to have a longer term solution. If we make something, just say we're using our computer to create a beautiful chair design or a new pair of heels, then what you would have to do is save that design onto the hard drive. And so the hard disk drive, it's used as a longer term storage solution, and it is much, much cheaper in terms of the price per storage capacity. So the hard drives are a great storage solution, but the only thing is that relative to RAM, they are much, much slower. So there's a bit of a compromise, and you shouldn't really be using the hard drive for short-term memory. However, there are new types of hard drives coming out, special ones. Some are called SSDs, and these are like a super fast type of hard drive, and they can sort of be used for the short-term memory. Like the new M1 Apple laptops, they tend to use the SSD inside it, the hard drive inside it, as a short-term memory when you run out of the RAM. So sometimes a hard drive is used for short-term memory, but it's usually, you'll get much better performance from your computer if you just have lots and lots of RAM. So now that we know about the CPU and the memory, now we can start to learn really about the gist of programming. And we talked about this a little bit in the first video, but now we're going to go a bit more in depth, which will set us up for programming in the next video that you'll watch. To make a computer do what you want, you have to give it the most precise instructions. That's because computers at the moment, computers are kind of dumb, and they only understand what they know. You know, humans and other animals and organisms, we have a system of neurons, and neurons arranged in neural nets, which help us learn new things. Like when you're listening to this video now, your brain is assembling lots of different patterns to try and make sense of what I'm saying and organize it into your brain. Now, a general purpose computer cannot do this, but recently we've been looking at incorporating some of those ideas of the way that animal brains work and incorporating them into what we call artificial intelligence. And these are getting very clever at doing specific tasks, but we still quite haven't cracked how to make artificial intelligence general purpose. So it's kind of similar to the pattern that we saw with early digital computers. They were all single purpose, and then they became general purpose, and we're seeing the same thing occur with artificial intelligence. So perhaps by the time you finish school and you're working, you might see some of the hints of general artificial intelligence. But for now, you have to give the computer precise instructions. So what I'm saying is, in the future, maybe 50 years, you won't need to give the computer precise instructions. You could say, go make me a cup of tea, and it will understand what you mean. As we learned in the first video, programming is about giving the computer a list of instructions, and these instructions have to be in a language that the computer can understand. So computers understand zeros and ones, but humans are not very good at understanding what lots and lots of random zeros and ones could mean. And scientists and technologists have created other languages like Python or JavaScript. They're two very, very popular languages at the moment, and they kind of resemble an English or a human language. And when we write them, these need an interpreter or a translator, and they take the Python and JavaScript instructions and then convert them into the binary code, the machine code that the computer natively understands. So to make a computer do something, you have to type in instructions that it understands. So the instructions can be a direct command, which gets carried out straight away. So you could tell the computer to add x plus y or add 1 plus 2. And you push return or enter, and the computer will tell you the answer. Or you can give it a list of instructions, which the computer will then save to the long-term memory, the hard drive. And when you're ready, you can tell it to run that list of commands. In the example to the left here, what we're seeing is this is an ancient language called BASIC, and BASIC had numbers that the computer had to follow out in that order. So the first one says print, 1 robot is great. Then the second line starts with 20 saying two robots are great, and then 3 robots are fantastic. So if you were to run that program, it would display all of those sentences whenever you were ready to see them. So we need to understand how the instructions break down. So let's just pretend that we wanted to write a program for fixing a hole in our tire. So in our bike tire or car tire, you need to break the whole process down into small chunks. So the first step would be something like remove the wheel, and then you would want to find the tire lever. Then you can remove the tire, and then you can mend the puncture. So there's 4 steps here, but each of those steps then needs to be broken down into smaller steps, and perhaps some of those will need smaller steps. And what we're really doing is we're breaking each of these down into the smallest step that the computer language can understand. And that's how we get computers to carry out all of the different tasks, from being able to detect cancer to controlling traffic lights when you're on the road. Any computer, these sentences, unless it's a general artificial intelligence-based computer, all the rest of the computers are not going to. So again, the computer cannot understand instructions that are written in a human language. So if we gave the computer to understand that, we have to use a specific computer language like JavaScript, Python, C or C++ or Java. And what those do are they are like an in-between language that humans can understand, but also computers can understand. So all the work inside the computer is done with codes, and those codes are like tiny pulses or loops of electricity. So in the first video that you watched, I tried to explain the 1s and 0s as looping, like electricity that goes around and around in a loop, right? And sometimes that looks like a pulse if you were to measure it with like an oscilloscope. And you write the instructions using a computer language. So that's a language that a human can understand and a computer can understand. And then that language is then translated into machine code, which is the 1s and the 0s. I mean, there are some people who can understand the ones and the zeros. There's whole big data sheets and books that explain how to do it, but it's a very, very slow and clunky way to write code. So each piece of information in the machine code is represented by patterns of pulses. So computer code is written inside the computer's memory as a 1 for like a high energy pulse and a 0 for a low energy pulse. Each piece of information in machine code is represented by these patterns of pulses. You could write programs in machine code, but it would be very difficult and take a long time. And also, I've tried this, it's very hard to see errors. It's like trying to find a needle in a haystack. A long time ago, when the computers were much smaller and they had less memory, it was a lot easier to write in machine code. And a lot of my early programs were written this way because there was no other higher languages available for the types of computers I was using. These days, most of you are very lucky to have a computer that has high-level language. So high-level language look like human languages. So we've got human languages like English and Mandarin. And these are high level. And as you get harder and harder, as you get more and more like machine code, which are 1s and 0s, the languages are set to be more low level. So there's a high level. So a language like Python, that's quite high level. A language like C is a bit lower. And then my favorite language is assembly, which is very, very close to the machine code level. But it's very, very tricky to understand for the first time because it requires you to know all about how the CPU is built and what the different buildings inside the CPU look like. Inside the processor, it's actually like a giant city. And if you've ever looked at Google Maps, it's like the CPU has different buildings for different things, and the different codes of ASM talk to different buildings. But that goes way beyond the scope of anything you do in year 7 or 8. And perhaps if you were interested, you could study this in year 11 and 12 with software design or in IPT, Information Processing Technology. So I've mentioned this before, there are hundreds of different high-level languages, and many of them are specifically designed to do a certain type of task, but others are very general purpose as well. And you can also make up your own. The most popular languages I can think of today are JavaScript, Python, C, Java, which is different to JavaScript, and Java's like brother or sister, C#, Fortran, which was used to power this Voyager spacecraft in the 70s. There's the Apple, Object-C and Swift languages, and Scratch, which you might already know after having done it in primary school. These days, most devices will have been coded using one of these languages. Something like a washing machine, it might be called a smart washer. It has lots of little sensors built in, and those sensors are connected to a brain. So there's sensors and they're connected to a CPU, like a brain with some memory. The washing machine CPU and memory will monitor the way that the drum inside the washing machine spins, the amount of force and torque exerted, all these things designed to make a better clothes washing machine. And of course, the marketing teams and advertising teams love these little ways to help sell those products. So you see computer languages everywhere. One of my favorite things to do is to see how other people will take this game from the 90s called Doom and see if it can run on a device that was not meant to run Doom. So here what we're seeing is a smart lamp bought from IKEA, and someone's connected a screen up to the lamp and imported the C code from Doom to see if the lamp could run it, and it worked. You can see examples of this online, but by the time you read this, IKEA might have taken down all of the ways to do it. At first glance, computer languages will look really foreign and they might appear difficult, but then other languages, like human languages, like the Finnish that we can see up here, or if you know any other languages, they can all seem quite foreign as well. And what we need to do is remember that we're starting from the most basic and we work our way up to more and more complexity. We would never attempt to throw you in the deep end of the pool when it came to learning a new language. In addition to programming a computer, there are lots of other subjects and activities in which you need a special language. So for instance, in this example up here, we see that mathematics has its own special language. Here you've got sine and cos, which you'll learn about soon in maths, and there are lots of other funky things in maths. You might eventually see some matrix maths that looks like this if you go on to do computer science, but also other activities like playing chess. This has its own language. Maybe some of you play chess and you've seen what this is. Do you know what each one of these steps describes in terms of playing chess? This describes the movement of the different pieces on the chessboard, and it tells you how the game will play out. And so people record chess games being played, and that's the notation that they use in order to record them. Music also has its own code, and you might be familiar with something like this if you play an instrument yourself, and it will have its own code. And to someone who's never played music before, this could look weird and foreign too. Can you think of any others? Maybe write them in a comment below in this post so that we can see what other types of codes you might have. Maybe some sports that you play have a code, like American football has a very strategic basis, and they have a code for assembling the players into formation. What other activities can you think of that have a code? I found this one, which is very interesting. It's called Laber notation. So if you like dancing and you really, really want to study this and you go study this at university, you might learn this style of dancing code. It's like a dancing language, and it uses these symbols to show you how you're meant to move different parts of your body across the room that you're dancing in. Isn't that crazy? So a program is like the rules for a game or the recipe when you're making a cake. If you don't follow the rules, then you can't play the game properly. And if you don't follow the recipe for making your cake, it might taste horrible. In the same way, the results you get from a computer program depend on the instructions that you give it. If you write a program for your computer, you first need to study what you want to do very carefully and work out the main steps needed to achieve the result that you want. So let's just imagine that we want to write a program that could tell a robot to go post a letter. Now, if we had generalized artificial intelligence, we could just say, "Hey robot, please post this letter." and the robot will do it. But in this case, if you give the instruction, please post this letter to any ordinary computer or a phone, it's not going to understand what it means. It's just too much advanced a concept. In order for that to happen, we would need to train the robot from a young age to understand what the mail is and what a letter is and how there are different mailboxes and how to get from point A to B. There's a lot going into there for it to understand how to do this without us telling it. So instead, we need to break down the instructions. So to do that, we might think that the robot will have to leave the home, post the letter, and then come back home. The computer needs instructions for every stage. Otherwise, it will get stuck. So if we break this down, as I said, we have these three general directions, right? So the first one will be leave home, post the letter, and come home. And when we've got leave home, that can be broken down into walk to the front door, open the door, go out and close the door, find the post box. Once it gets to the post box, then it runs the post letter instructions. So that will be to hold the letter in the hole and then let go of the letter. And then it does everything in the come home instructions. In this example, you see the robot crashing through the wall because we haven't told it to look out for walls. So the robot will attempt to follow your instructions even if they're wrong or incomplete. Mistakes in a program are called bugs. And a bug will often result in something weird going on or nothing going on. So that means you need to go back to the code that you've written and see if you can find where the problem might be. When you're writing a program, it sometimes helps to draw a diagram like the one shown on the right. And the diagram shows the flow of processing control that your program will undertake. This diagram is known as a flowchart because it shows the flow of data and processing through the system. So this flowchart that we've got here will read two numbers and then add them and then display the number to the user. A flowchart has lots of different shaped boxes for each of the different steps in the program. The beginning and the ends of the flowchart have rounded edges, and each of the instructions that tell the computer to do something, they're in rectangular boxes. And if the computer needs to make a decision, like, is it raining outside? If it's yes, then we go this way, and if it's no, we go that way. So decisions are represented with diamonds and the lines with arrows on them. And the arrows show the direction, the flow of the data. So we're showing you the flowchart because, like in every TAS subject, it's so important that you plan your designs with pencil and paper first before you even touch a computer. And this goes for every task you might do. Even if it's a design using Illustrator, InDesign or Canva, you need to sketch this out on a piece of paper first, and then you go onto the computer and you build your prototype that way before building the final design product. After watching these 3 videos, you should now have a very solid understanding of the computer concepts needed to code in any language. Languages that resemble English or use blocks, like visual blocks, like the ones you see in Scratch or in Minecraft. These languages are very easy to learn, but they're very slow. They've been specifically designed to teach programming, but you would never find a commercial application written in one of those languages. The less a language looks like English and some of the other languages, the faster it will run, but the harder it is to learn. Once you learn one language, it's very easy to pick up newer languages. The first language is always the hardest to learn. So here I've shown you examples of different computer languages, and we start any language with the famous task called Hello World. And Hello World is traditional. It's the first program that you write in any language. And what it's designed to do is show you how to get an output onto the screen. Because as we remember, the basis of any computer system is to have an input, and the input is thought about, and then it displays an output. So in this example, up here we have Python, and in Python you type the words print, and then you put in inverted commas what you would like to be displayed on the screen. And like I said, traditionally we say hello world, okay, because it's like the computer saying hello to the outside world. The next example here, this is JavaScript. And JavaScript has become very popular because it's an online language. All web browsers understand JavaScript. So its use and adoption has become very spread. The next language we have here is Fortran. And Fortran was one of the first ever computer languages that resembled English. And you'll notice that we're starting to use things like this variable here, and it starts to get a bit less looking like English because of that's asterisk there. And then you've got a language like C, and C here is using a function, and that function is print. And we've got lots of these little weird symbols that, again, make it faster for the computer to run. But sometimes having these little symbols here, you tend to forget, beginners will tend to forget what they mean and what they do. But in general, most of these languages are quite easy to learn. We have these higher level languages that help us learn them. Something like as easy as print hello world that you get with Python. Thanks for watching, everyone. This is an example of hello world in one of my favorite languages, and this language is 6502 assembly. And assembly language is one step up from machine code. I usually don't like working in machine code. It's very cumbersome and prone to lots of errors. But ASM is much cleaner, and it's super efficient. It's very fast, but it's very hard to learn. When I was learning this, when I was very little, it was much easier to learn because the CPUs and the computers back then were much smaller and they were slower, and you could really get inside the CPU to see what was going on. But as computers have become more and more complex and faster and lots of layers added on, it's become much more difficult to learn assembly for those computers. And instead, but again, that's just a look at the history and where we've come from these sort of older languages that don't look anything like a human language to